Process Performance and Quality. Chapter 6. 1. Process Performance and Quality. How process performance and quality fits the operations management philosophy. Operations as a competitive weapon. Operations strategy. Project management. Process strategy. Process analysis. Process performance and quality. Constraint management. Process layout. Lean systems. Supply chain strategy. Location. Inventory management. Forecasting. Sales and operations planning. Resource planning. Scheduling. Quality at Crowne Plaza, Christchurch. The Crowne Plaza is a luxury hotel with 298 guest rooms, 3 restaurants, 2 lounges and 260 employees to serve 2,250 guests each week. Customers have many opportunities to evaluate the quality of services they receive. Prior to the guest's arrival, the reservation staff gathers a considerable amount of information about each guest's preferences. Guest preferences are shared with housekeeping and other staff to customize service for each guest. Employees are empowered to take preventative, and if necessary, corrective action. Costs of poor process performance. Defects, any instance when a process fails to satisfy its customer. Prevention costs are associated with preventing defects before they happen. Appraisal costs are incurred when the firm assesses the performance level of its processes. Internal failure costs result from defects that are discovered during production of services or products. External failure costs arise when a defect is discovered after the customer receives the service or product. Total quality management. Quality, a term used by customers to describe their general satisfaction with a service or product. Total quality management, TQM, is a philosophy that stresses 3 principles for achieving high levels of process performance and quality. Customer satisfaction. Employee involvement. Continuous improvement in performance. TQM Wheel Customer Satisfaction Service/Product Design Process Design. Employee involvement. Continuous improvement. Customer satisfaction. Process design. Purchasing. Service/product design. Problem-solving tools. Benchmarking. 2. Customer satisfaction. Customers, internal or external, are satisfied when their expectations regarding a service or product have been met or exceeded. Conformance, how a service or product conforms to performance specifications. Value, how well the service or product serves its intended purpose at a price customers are willing to pay. Fitness for use, how well a service or product performs its intended purpose. Support, support provided by the company after a service or product has been purchased. Psychological impressions, atmosphere, image, or aesthetics. Employee involvement. One of the important elements of TQM is employee involvement. Quality at the source is a philosophy whereby defects are caught and corrected where they were created. Teams, small groups of people who have a common purpose, set their own performance goals and approaches, and hold themselves accountable for success. Employee empowerment is an approach to teamwork that moves responsibility for decisions further down the organizational chart to the level of the employee actually doing the job. Team approaches. Quality circles, another name for problem-solving teams, small groups of supervisors and employees who meet to identify, analyze, and solve process and quality problems. Special purpose teams, groups that address issues of paramount concern to management, labor, or both. Self-managed team, a small group of employees who work together to produce a major portion, or sometimes all, of a service or product. Continuous improvement. Continuous improvement is the philosophy of continually seeking ways to improve processes based on a Japanese concept called Kaizen. Train employees in the methods of statistical process control, SPC, and other tools. Make SPC methods a normal aspect of operations. Build work teams and encourage employee involvement. Utilize problem-solving tools within the work teams. Develop a sense of operator ownership in the process. The Deming Wheel Plan Do Check Act Cycle. 9. Statistical Process Control. Statistical process control is the application of statistical techniques to determine whether a process is delivering what the customer wants. Acceptance sampling is the application of statistical techniques to determine whether a quantity of material should be accepted or rejected based on the inspection or test of a sample. Variables, service or product characteristics that can be measured, such as weight, length, volume, or time. Attributes, service or product characteristics that can be quickly counted for acceptable performance. Sampling. Sampling plan, a plan that specifies a sample size, the time between successive samples, and decision rules that determine when action should be taken. Sample size, a quantity of randomly selected observations of process outputs, sample means and the process distribution. Sample statistics have their own distribution, which we call a sampling distribution. Sampling distributions. A sample mean is the sum of the observations divided by the total number of observations. Sample mean, where 11 equals observations of a quality characteristic such as time. N equals total number of observations. X equals mean. The distribution of sample means can be approximated by the normal distribution. 4. Sample range. The range is the difference between the largest observation in a sample and the smallest. The standard deviation is the square root of the variance of a distribution, where equals standard deviation of a sample. N equals total number of observations. 11 equals observations of a quality characteristic. X equals mean. Process distributions. A process distribution can be characterized by its location, spread, and shape. Location is measured by the mean of the distribution and spread is measured by the range or standard deviation. The shape of process distributions can be characterized as either symmetric or skewed. A symmetric distribution has the same number of observations above and below the mean. A skewed distribution has a greater number of observations either above or below the mean. Causes of variation. Two basic categories of variation in output include common causes and assignable causes. Common causes are the purely random, unidentifiable sources of variation that are unavoidable with the current process. If process variability results solely from common causes of variation, a typical assumption is that the distribution is symmetric, with most observations near the center. Assignable causes of variation are any variation-causing factors that can be identified and eliminated, such as a machine needing repair. Assignable causes. The red distribution line below indicates that the process produced a preponderance of the tests in less than average time. Such a distribution is skewed, or no longer symmetric to the average value. A process is said to be in statistical control when the location, spread, or shape of its distribution does not change over time. After the process is in statistical control, managers use SPC procedures to detect the onset of assignable causes so that they can be eliminated. Location, spread, shape. Copyright 2007 Pearson Education. Control charts. Control chart, a time order diagram that is used to determine whether observed variations are abnormal. A sample statistic that falls between the UCL and the LCL indicates that the process is exhibiting common causes of variation, A statistic that falls outside the control limits indicates that the process is exhibiting assignable causes of variation. Control chart examples. Type 1 and 2 errors. Control charts are not perfect tools for detecting shifts in the process distribution because they are based on sampling distributions. Two types of error are possible with the use of control charts. Type I error occurs when the employee concludes that the process is out of control based on a sample result that falls outside the control limits, when in fact it was due to pure randomness. Type 2 error occurs when the employee concludes that the process is in control and only randomness is present, when actually the process is out of statistical control. Statistical process control methods. Control charts for variables are used to monitor the mean and variability of the process distribution. R chart, range chart, is used to monitor process variability. X chart is used to see whether the process is generating output, on average, consistent with a target value set by management for the process or whether its current performance, with respect to the average of the performance measure, is consistent with past performance. If the standard deviation of the process is known, we can place UCL and LCL at Z standard deviations from the mean at the desired confidence level. UCL equals X plus A2R and LCL X equals X, A2R. Control limits. The control limits for the X chart are UCL equals X plus A2R and LCL X equals X, A2R. Where X equals central line of the chart, which can be either the average of past sample means or a target value set for the process. A 2 equals constant to provide 3 sigma limits for the sample mean. Dash equals dash equals. The control limits for the R chart are UCLR equals D4R and LCLR equals DARE where R equals average of several past R values and the central line of the chart. D3, D4 equals constants that provide 3 standard deviations, 3 sigma, limits for a given sample size, calculating 3 sigma limits. Table 6.1. West Allis Industries Example 6.1. West Allis is concerned about their production of a special metal screw used by their largest customers. The diameter of the screw is critical. Data from 5 samples is shown in the table below. Sample size is 4. Is the process in statistical control? 1. West Allis Industries Control Chart Development. Example 6.1. 0.5027 to 0.5009 equals 0.0018. Sample. Number 1 2 3 4 RX. 1 0.5014 0.5022 0.5009 0.5027 0.0018 0.5018 2 0.5021 0.5041 0.5024 0.5020 3 0.5018 0.5026 0.5035 0.5023 4 0.5008 0.5034 0.5024 0.5015 5 0.5041 0.5056 0.5034 0.5039. Special metal screw. Underscore. 0.5014 plus 0.5022 plus 0.5009 plus 0.5027/4 equals 0.5018. 4. West Allis Industries completed control chart data. Example 6.1. Special metal screw. Equals. Underscore. Sample. Number 1 2 3 4 RX 1 0.50 1 4 0.5 0 2 2 0.5 0 0 9 0.5 0 2 7 0.0 0 1 8 0.5 0 1 8 2 0.5 0 2 1 0.5 0 4 1 0.5 0 2 4 0.5 0 2 0 0.0 0 2 1 0.5 0 2 7 3 0.5 0 1 8 0.5 0 2 6 0.5 0 3 5 0.5 0 2 3 0.0 0 1 7 0.5 0 2 6 4 0.5 0 0 8 0.5 0 3 4 0.5 0 2 4 0.5 0 1 5 0.0 0 2 6 0.5 0 2 0 5 0.5 0 4 1 0.5 0 5 6 0.5 0 3 4 0.5 0 4 7 0.0 0 2 2 0.5 0 4 5 R equals 0.0021. X equals 0.5027. 11. R chart control chart factors. West Allis Industries. R chart control chart factors. Example 6.1. Factor for UCL, factor for factor. Size of and LCL for LCL for UCL4. Sample X charts are charts. N, A2, D3, D4. 21.88003.267. 31.0230.2.575. 40.7290.2.282. 50.5770.2.115. 60.4830.2.004. 70.4190.076.1.924. 80.3730.136.1.864. 90.3370.184.1.816. 10.0.3080.223.1.777. R equals 0.0021. D4 equals 2.282. D3 equals 0. UCLR equals D4R equals 2.282. 0.0021 equals 0.00479 inches. LCLR equals D0. 0.0021 equals 0 inches. 13. West Allis Industries range chart. Example 6.1. 20. X chart control chart factor. West Allis Industries. X chart control chart factor. Example 6.1. Factor for UCL, factor for factor. Size of and LCL for UCL4. Sample X charts are charts. N, A2, D3, D4. 21.88003.267. 31.0230.2.575. 40.7290.2.282. 50.5770.2.115. 60.4830.2.00. R equals 0.0021. A2 equals 0.729. X equals 0.5027. Equals. UCL equals X plus A2. R equals 0.5027 plus 0.729. 0.0021 equals 0.5042 inches. LCL X equals X, A2 R equals 0.5027 to 0.729, 0.0021 equals 0.5012 inches. Equals. 13. West Allis Industries X chart example 6.1. Sample the process, find the assignable cause. Eliminate the problem, repeat the cycle. 27. Application 6.1. Application 6.1. Application 6.1. Process capability. Process capability is the ability of the process to meet the design specifications for a service or product. Nominal value is a target for design specifications. Tolerance is an allowance above or below the nominal value. Process capability 20-25 30 minutes upper specification lower nominal value. Process distribution. Process is capable. 18. Process capability 20-25 30 minutes upper specification lower nominal value. Process distribution. Process is not capable. 18. Effects of reducing variability on process capability. Lower specification. Mean. Upper nominal value. 6 sigma. 4 sigma. 2 sigma. 22. Process capability index, CPK. Process capability index, CPK, is an index that measures the potential for a process to generate effective outputs relative to either upper or lower specifications. CPK equals minimum of upper specification, X. 3s. X, lower specification. Equals. We take the minimum of the two ratios because it gives the worst case situation. 33. Process capability ratio, CP. Process capability ratio, CP, is the tolerance width divided by 6 standard deviations, process variability. CP equals upper specification, lower specification. 6. 33. Using continuous improvement to determine process capability. Step 1. Collect data on the process output, calculate mean and standard deviation of the distribution. Step 2. Use data from the process distribution to compute process control charts. Step 3. Take a series of random samples from the process and plot results on the control charts. Step 4. Calculate the process capability index, CPK, and the process capability ratio, CP, if necessary. If results are acceptable, document any changes made to the process and continue to monitor output. If the results are unacceptable, further explore assignable causes. Intensive Care Lab Example 6.5. The intensive care unit lab process has an average turnaround time of 26.2 minutes and a standard deviation of 1.35 minutes. The nominal value for this service is 25 minutes with an upper specification limit of 30 minutes and a lower specification limit of 20 minutes. The administrator of the lab wants to have 4 sigma performance for her lab. Is the lab process capable of this level of performance? Upper specification equals 30 minutes. Lower specification equals 20 minutes. Average service equals 26.2 minutes. Equals 1.35 minutes. 33. Intensive Care Lab Assessing Process Capability. Example 6.5. Upper specification equals 30 minutes. Lower specification equals 20 minutes. Average service equals 26.2 minutes. Equals 1.35 minutes. CPK equals minimum of upper specification, X. 3s. X, lower specification. Equals. CPK equals minimum of 26.2 to 20.0. 3 1.35. 30.0 to 26.2. CPK equals minimum of 1.53, 0.94 equals 0.94. Process Capability Index 33. Intensive Care Lab Assessing Process Capability. Example 6.5. CPK equals upper specification, lower specification. 6. CP equals 30 to 20. 6 1.35 equals 1.23. Process Capability Ratio does not meet 4, 1.33 CP, target. Before process modification. Upper specification equals 30.0 minutes, lower specification equals 20.0 minutes. Average service equals 26.2 minutes. Equals 1.35 minutes. CPK equals 0.94. CP equals 1.23. After process modification. Upper specification equals 30.0 minutes, lower specification equals 20.0 minutes. Average service equals 26.1 minutes. Equals 1.2 minutes. CPK equals 1.08. CP equals 1.39. 33. Application 6.4. Application 6.4. Six Sigma. Six Sigma is a comprehensive and flexible system for achieving, sustaining, and maximizing business success by minimizing defects and variability in processes. It relies heavily on the principles and tools of TQM. It is driven by a close understanding of customer needs, the disciplined use of facts, data, and statistical analysis, and diligent attention to managing, improving, and reinventing business processes. Six Sigma Improvement Model. Determine the current process characteristics critical to customer satisfaction and identify any gaps. Quantify the work the process does that affects the gap. Use data on measures to perform process analysis. Improve, modify or redesign existing methods to meet the new performance objectives. Monitor the process to make sure high performance levels are maintained. Six Sigma Implementation. Top-down commitment from corporate leaders. Measurement systems to track progress. Tough goal setting through benchmarking best-in-class companies. Education. Employees must be trained in the whys and how-tos of quality. Communication. Successes are as important to understanding as failures. Customer priorities. Never lose sight of the customer's priorities. Six Sigma Education. Green Belt, an employee who achieved the first level of training in a Six Sigma program and spends part of his or her time teaching and helping teams with their projects. Black Belt, an employee who reached the highest level of training in a Six Sigma program and spends all of his or her time teaching and leading teams involved in Six Sigma projects. Master Black Belt, full-time teachers and mentors to several black belts. International Quality Documentation Standards. ISO 9000. A set of standards governing documentation of a quality program. ISO 14000. Documentation standards that require participating companies to keep track of their raw materials use and their generation, treatment, and disposal of hazardous wastes.